So far we introduced the maximum margin classifier, which is a classifier for, which is a linear classifier for linearly separable data. Next, we introduced the support vector classifier, which is still a linear classifier, but which allows for data to be not linearly separable. So effectively, this can already deal with the kind of most general example of data, which is kind of mixed, like as you saw in kind of this example here. So first I had the situation where my data looked like this, and I kind of found a classifier of this type. This was the maximum margin classifier. Then I extended the case to data where kind of I have mixed data is not linearly separable anymore, but I still want to be able to find a classifier which is still separable. Now when we go to support vector machines, we now allow this classifier to be non-linear. For example, in this case it might be a function which looks like this. So support vector machines are the non-linear extension of support vector classifiers. And the basic idea is kind of hard to get an intuition mathematically, so I will show it in some pictures. But the idea is we are still going to do a support vector classifier, we are still going to do a linear classifier, but we are going to do it in a higher dimensional space. So we're kind of trying to map our original space, the predictor space, which is p-dimensional, into a higher dimensional space in which we find the linear support vector classifier, but then projecting it back down into the original lower dimensional space. This classifier can actually look non-linear, and it will provide us with a non-linear decision boundary. So this might sound a bit complex. It actually is quite complex mathematically, but I think we can nicely illustrate it in an example here. So imagine I have a two-dimensional space, a two-dimensional predictor space. I have variables x1 and x2 here, and this is my data here. I have data of one class here and data of another class here outside, say. And here obviously the decision boundary I can see with this blue circle, it's actually a nice circular decision boundary. This is kind of the data which nicely separates the kind of classes of two types. Now I have all classes of one type being inside and all classes of the other types, the plus one type, being outside. But the boundary is non-linear, it's actually a circle there. Whereas if I would be trying to fit a kind of support vector classifier, I could only do something like this, or maybe something like this, but then anything on the one side of the boundary would be classified, say, as plus one label, and everything on the other side as the minus one label. So that's not very good. But how could I potentially get such a non-linear decision boundary? And here's an example. If I look at the previous data, if I do a kind of coordinate mapping here, so this phi here maps my original kind of 2D space, so this is kind of 2D, into a 3D space. So I'm going from 2D into 3D by effectively introducing a new variable here, this last one, which is just a function of the other two variables, and here I'm kind of squaring it. So if you would kind of draw this mapping here, you can actually see that the plane, the kind of 2D plane of this coordinate system here, this kind of 2D plane is now mapped into this cone here. So what I'm actually doing, I'm kind of taking this space, and let me see whether I can find some piece of paper here. I'm taking this kind of this 2D data, I'm basically kind of warping it up into this cone-like structure basically. Now kind of all the data points which were kind of on all the data points which were here on the kind of inside region, they're now mapped here, whereas all the data points which were on this outside region here, they're now mapped to this kind of bit of the cone here. So this is this kind of what this mapping does. If I plot those new variables here, x1, x2, and here have this new z variable, if I plot it in this 3D space, and this is something maybe you have to believe me that kind of this is what this mapping does, but I will actually kind of put my original my original 2D space inside of this 3D space, and it will be some form of hyperplane in this or some hyperspace in this 3D space, which has exactly this cone-like structure. And now, given that my my data points, which were kind of in the inside there, are now on the one hand of the cone, namely here, and the other ones on the other side of the cone, if I can now find a linear model, exactly this plane which is indicated there in the figure, I can find this linear model which exactly classifies the data, all the red ones on one hand and all the kind of green or blue ones on the other hand. And if you work out the math, you can actually see that this linear decision boundary here, I mean, you can already see from the figure that this linear decision boundary, this plane here, in this original space, it will kind of be inducing this circle here, where this plane cuts this cone, it will be a circle. And this circle is exactly what the decision boundary looks like in this lower dimensional space here. So here I've actually seen that if I can map the model to a high dimensional space, I can potentially find a linear classifier there, which then gives me a nicely non-linear model in the lower dimensional space. And this is exactly the intuition behind the support vector machine, which is a nonlinear extension. It's still linear, but linear in some higher dimensional space. And as we can see later, we can make it more and more dimensional, which in a sense makes my classifier more and more nonlinear potentially. So I can even go so far as to map it to an infinite dimensional space, which is something rather kind of funny to think about there. Now the picture might be, well, it looks a bit less clear now, but I hope the intuition behind it is clear. But the math can be quite complicated. I don't want to go through the details there, so it's actually a bit beyond the kind of math we can do in this course, but I just wanted to give you some intuition of where it comes from, basically. So what we know is that if we usually define a support vector classifier, the linear model, then kind of my decision boundary is given by something like f of x equal to 0, and this f of x here is some function which is beta 0 plus, and then I have like beta vector times x vector here. And let's just recall that so those betas I have found using my optimization procedure, and let's just recall that by this dot I just mean the standard dot product here. You might also write kind of transpose here if that's clearer there. So it's just the standard vector product, which is basically row vector times column vector here. And interestingly, obviously the betas are determined using my data points. So given my data points, I will find the betas. Remember, we did this maximization problem where we or the minimization problem where we minimized the omegas or we maximize the margin over betas there. So kind of remember that beta and omega were just easily related. So kind of my optimization problem gives me my betas, and they obviously depend on the data. Different data will give me different betas in the fitting procedure. If I have different data, I will find a slightly different different plane here. Remember, here's the data. Now the betas just define this line. So if I have different data points, that defines a plane. So if I have different data points, I will get different betas there. And you can actually see that the solution to the optimization problem will actually show you this thing can be written, and this bit you have to believe me because the math is actually a bit complicated to derive this, but this can be written as some sum over all data points is important here. N is the number of data points, not the dimension of the space here, times some coefficients which are called alpha, and here I have this inner product now between my data points and now my vector x here. So this can actually be shown that once I find this beta, these betas will effectively be proportional to the betas will basically be represented by this sum here. So this is effectively my my kind of beta transpose, if you like so. But that's effectively what you can show mathematically, that you can write it in this way. So this is kind of important for the math, because here you have first of all, it's just the sum over all the data points and not the dimension, and you have this inner product here of the two vectors, and this is where the generalization comes in. Now when we do write this, when we now go, this is the kind of support vector classifier, the decision boundary. Now if we go to the support vector machine, what we do is we kind of take this f of x equal to beta 0. We have the same expression, but now we replace those vectors here by this transformation. We call that, if you go back to the previous slide, here we had this original vector x here, and we're kind of replacing x by this transformation phi of x, which is the second expression here. So what I'm doing here, I'm actually taking phi of xi transpose phi of xi. So this is what I'm kind of doing. So the change is really here in doing this mapping. So here, rather than taking the original inner product between the two vectors, I'm taking the inner product of this transformed, of this higher dimensional space. And before it was in this example above, the inner product would be about a two-dimensional space, but now I'm going to a three-dimensional space. And now there's some more interesting math comes in. So this is just how you do it in generally, but kind of obviously this still involves this inner product, which potentially can be very high dimensional. If this is kind of 100,000 dimensional space, I would have to kind of multiply 100,000 dimensions. This doesn't sound very helpful, but you can actually see that there's another piece of math which comes to the rescue, that actually I can write now this inner product. So this thing here, phi of xi times phi of x, this thing I can actually write as some kernel of xi and y. I will be talking a little bit what these kernel functions are, but for each phi, and you can show this mathematically, for each phi there exists a kernel which does this mapping. And if I have this, I can furthermore write this expression here as alpha I times the kernel of xi comma x here. So effectively, when I do support vector machines, I don't have to think explicitly about those phi. So I don't have to find a phi. Like here, you might ask me, well, where does this phi here come from? This phi here, obviously you can see in the picture that this phi you could work out corresponds to this cone. And obviously if I do it like this, I can find the nice linear boundary in this high dimensional space. But in general, you'll ask me, well, how the hell do you come up with those phis here? And the answer is that actually we do not kind of find these phis explicitly, but rather we work with these kernels k, and we use the mathematical fact that effectively for each phi there exists a kernel which matches this phi, and you can even kind of work it out kind of effectively which would be the kernel corresponding to this phi, and we will talk about this potentially in a little bit. But just to go back, so once we have seen this mapping, I can now effectively define my nonlinear decision model by just saying I will introduce a kernel. This kernel will map myself to a high dimensional space. I will now fit a support vector classifier in this high dimensional space and map back to the lower dimensional space where we'll have a nonlinear decision boundary. So this is basically the recipe. It sounds a bit complicated, but you don't need to kind of know all the details, because really if you want to do all the math, it's quite some heavy math there, and you know why it was a kind of Russian mathematicians who came up with that after you have worked yourself through the math. What is important for you to know is that there are kind of different kernels I could use. For example, if I just say the kernel is just the inner product, then effectively I have back the original model. So if K is just the inner product, then I have exactly the same as here. This thing here is just K being the inner product. Then I'm back at the original model and I have a linear model. So this kernel here will give me a linear model. Now, I could also now make it slightly nonlinear by introducing this kind of quadratic kernel here, which is just 1 plus the inner product to the power d. And, well, d is polynomial kernel, but if I choose d equal to 2, I would have a quadratic kernel. And you can see already a little bit how this comes about. So I can actually see that the quadratic kernel is quite similarly related to this mapping here. So here I have phi being this mapping. So if I would be asking, for example, in this case, what would be this inner product? What would be phi of x, phi of y for this example, which I've given on the previous slide? So what would I have? I had like x1 squared, x2 squared, square root 2, x1, x2 transpose, and then here I had y1 squared, y2 squared, square root 2 of y1 times y2 basically. But if you work this out, you will obviously get something like x1 squared times times y1 squared plus x2 squared times y2 squared plus 2 x1, x2, y1, y2. But this thing here, actually, if I would work out what would be kind of x1 times x2, and then I have y1 times y2, this would obviously give me x1 times y1 plus x2 times y2. And now actually if I would square this expression here, I would have this thing squared, and I would get x1 y1 squared plus x2 y2 both squared plus 2 x1 y1 x2 y2. So you can actually see this is exactly the same. So what I've written here in this last expression is exactly the same as this. So I can see that for the function phi, which I've mentioned here, the kernel for that, now it's getting a bit messy, but the kernel for this phi is nothing else but the square kernel. So it's exactly like this one here for d equal 2 and without the 1. But I can actually see that I've seen an explicit example how I can map a given phi to a given k. What is important is that I do not have to know this mapping. All I'm doing is going to this previous expression, and I'm using this relationship here for f of x. I'm using this expression here, and all I'm doing is I'm working with this k. I'm never really working with the phi. I just wanted you to explain that the phi is related to the k, and this is how I can see how kind of k corresponds to mapping something to a higher dimensional space. Otherwise you might be asking me, how does k correspond to mapping to a higher dimensional space? But this is really kind of through the explanation which I've given above, you can see that. And one of the most common one used in practice is the exponential one, and this actually maps to a infinite dimensional space. well, this sounds a bit weird, but kind of you might have somewhat guessed it a little bit if you can see that all these previous ones, if you think about kind of Taylor expanding it in this dot product here, then obviously this first one would be linear in this dot product. The second one would be kind of, well, to the power d in this dot product. If d equal 2 would be just quadratic there. But if I do a Taylor expansion of this exponential here, I will obviously get a Taylor expansion which is of infinite order, and this, roughly speaking, means that I'm getting an infinite dimensional space here. Now obviously infinite dimensional space is very flexible, but what helps me to control the model is this sigma here. You see this exponential is exactly the same as a Gaussian. It's called the exponential kernel. It's sometimes also called the radial kernel, and kind of the sigma is the width of this this Gaussian here. I mean, just to recall that this is some form of Gaussian bell, and the width of this thing is given by sigma here. And obviously you can think of it like this: if sigma becomes wider, my data points have more influence, whether if sigma becomes narrower, there's less influence. So the kind of wider sigma makes the model more stable than the smaller sigma, which allows for more wiggly lines. So sigma is again something I have to tune using hyperparameter optimization with the bias variance trade-off, but you can already see that sigma being larger means less flexibility, because everything is kind of more reaching out, more connected to each other, whereas sigma being smaller corresponds to a more flexible model, and this is how it's really related to each other. Now this is basically the theory of support vector machines. It's all about generalizing the support vector classifier to use those kernels, and I've kind of hopefully showed you that using these kernels is effectively equivalent to going to a high dimensional space, finding a linear decision boundary there, and then mapping it back. And we have already seen an explicit example in this figure that this will give me non-linear decision boundaries in the lower dimensional space. And here I can see an explicit example. So here I can see data really. So here I can see some data of class 1 basically here. Then there's some data of class -1 in the middle. And here I fitted a support vector machine with an exponential kernel to the data. The one on the right is also a support vector machine with an exponential kernel, or it's also called the radial kernel. But then the one on the right hand side is more flexible. The one on the left hand side is less flexible. This one here has a larger sigma, and this one here has a smaller sigma. Using a smaller sigma makes the model be kind of, the points have less influence to the other ones, and this makes the kind of decision boundary more wiggly. So here you can basically see how I effectively classified this model. It looks a bit funny that you can see that actually the decision boundary can be mapped to actually two different lines, which effectively meet up at infinity, if you like. So, but that's maybe a relevant comment here. And the dashed lines are still the margin there. So here would effectively, in the first one, I would classify everything which is inside of these boundaries here. I would classify as everything inside here is classified as -1, and everything outside here would be classified as +1 here, and the decision boundary would be those the lines there separating the red and the blue area here. And here's the same effectively, only now that I would classify everything inside here as -1, and everything outside here I would classify as +1 basically, where the decision boundary is just this area which separates the two regions. So this is really how the support vector machine works. Remember, support vector machine is just a support vector classifier in a higher dimensional space, but this generates me a nonlinear decision boundary, and I can kind of again tune the amount of nonlinearity I want to have through some hyperparameters. The hyperparameter could be, for example, this d here in the kind of quadratic or the polynomial kernel. The higher the d, the more nonlinear the model is. Or it could also be this sigma here. The smaller the signal, the more nonlinear the model would be. And again, I would have to do some cross-validation to find the best value of d or to find the best value of sigma, which gives me the optimal model here. And this is really all which I wanted to say about the support vector machine, and that brings us to the conclusion.